anything or just start?
Cool. Yeah.
Hello, my name is Trevor Goodwin, and my presentation today will be about how two age classes of Atlantic white cedar respond to ditching events in the Great Dismal Swamp. And special thank you to my co-authors, Dr. Robert Atkinson and Mitchell Doyle. So for the background for this project, Atlantic white cedar is a conifer that is native to the eastern United States, and it commonly lives in coastal saturated peatlands. And these environments are very high in anoxia, or lack of oxygen, and acid. And these trees are very tolerant to that. And because they are especially tolerant to those environments, they can thrive in monocultures with high sunlight requirements. Unfortunately, these trees have declined in their population since coastal or colonial times. They've been commonly used in lumber historically, and their land has been converted to agriculture farms. And more specifically to this project, their hydrology changes have changed due to sea level rise and ditching. And ditching is that foundation of many of its current decline, as the wetlands change to only temporarily saturated. These change the conditions of that high anoxia and high acid, and it allows for other species to come in and outcompete Atlantic white cedar. So this study is done in Great Dismal Swamp, which is obviously a swamp that is in Virginia and North Carolina. This has an ideal habitat for Atlantic white cedar. It has peatland soil, and it was established as a National Wildlife Refuge in 1974. However, this site has been known to have extensive ditching throughout its history, beginning in the 1760s. A very significant canal was dug in 1805, and specific to this study, there was a vast ditching effort between 1956 and 1971 that have lowered the water tables to the levels they are today. And more recently, there have been catastrophic events, including a hurricane and two major fires that have almost decimated the Atlantic white cedar abundance, now very scattered throughout this swamp. So with that one hurricane, this is the focus of the trees that we studied here in this project. So this first image is what the hurricane did to many stands of Atlantic white cedar. They are blown down, and this provided an opportunity for salvage logging to occur. So that's what the image on the right is. This takes us to our methods of obtaining data for these trees. So the salvage logging operations collected 106 trees that blew down in Hurricane Isabel in 2003. And of those 11 stands, we could split them up into two different groups. So 6 of the stands began growing in 1940, and their average age at the time of death was about 60 years old. And 5 of those stands began growing around 1920, with their average age to be about 80 at the time of death. And these two age comparisons allowed us to examine how the trees responded to the ditching events between 1956 and 1971, and how different age groups responded differently to that ditching period. So the methods of measuring these in terms of growth, the cross sections of the salvage logging trees were obtained, and their ring widths were measured for the tree rings. Each year was measured and graphed, and those provided a one-dimensional measurement. However, we wanted to look at a two-dimensional measurement. Then they were converted and calculated into basal area. So basal area interprets data for a form of how much area a tree added to its trunk within a whole year of growth. So that gives the two-dimensional that we're looking for. So this is a better map of how those were converted. The formula is there. You don't really need to understand it, but each year was measured in ring width and plugged into a formula that gave us a value for incremental basal area increment, which is the term we use for that. So they were converted into graphs. So the results are all graphs that show a comparison between the two different aged cohorts of trees. So this is a map of, or a graph of how each cohort average response to each year of climactic variable. So this is an incremental view of basal area. So this just shows each yearly growth of the older trees, which are in blue, and the younger trees, which are in red. So the first thing that I want to point out here is that the younger trees caught up to the older trees. There was a clear shift in how fast they were growing, and that lined up conveniently to the ditching period of that started in 1956. So, and then another interesting thing here is that towards the end of their lives in the 1980s and 90s, they had nearly matched growth in terms of climactic response to the situations in Great Dismal Swamp until they all died together. And then this is a conversion of that incremental graph into basal area, cumulative basal area increment. So that previous graph was then added on top of each other for each of these 11 sites. So this gives a total total tree area for each year as it progresses throughout its life. And you know, all 11 sites are here. It's a bit busy, but the one thing that I want to point out is that the top 5 growing sites, so the 5 lines that are higher than all the rest, are all members of the young cohort. So the younger trees grew faster, and this graph here gives a better example of that. So this is an average of the 6 sites that made up the young cohort and the 5 sites that made up the old cohort. The young cohort in red clearly shows that it grew much faster, much higher, much stronger, even though it was in the same area, yet grew, started its lives 20 years later. So these graphs are zeroed. Each tree is given essentially the same age, and they were progressed through their lives in the young cohort. And each site grew faster than the old cohort. And then that takes us to an examination of how they responded to the ditching. So the brackets I placed on this graph are the years that the ditching occurred, between 1956 and 1971. And for the old cohort, this graph, both graphs actually are sort of exponential growth. That's just how the trees grew throughout their lives. So the slope is always increasing. However, the slope before the ditching period and then after the ditching period for the old cohort does not seem to have a significant change in the terms that the ditching affected it specifically. It was just a natural progression of the trees growing throughout their lives. That is compared to the young cohort, which is in red, a very, very clear change in that bracket time frame of a almost flat curve before the ditches occur, and then even a greater slope of change in BAI for the young cohort after the ditching. So this shows that the ditching caused the young cohort to have a more extreme response to the stress of a lower water table. And then this, a similar graph, this is back to the incremental BAI. These trees are zeroed again so that we can compare them by age. The young cohort again takes off, separating itself from the older cohort around 12 to 15 years old. And then after the ditching took place, the young cohort actually plateaued in terms of how much growth it was putting on its area each year. this was, I believe we determined that to be a genetic maximum for how much it grew. So the ditches affected the young cohort so much so that it reached its maximum growth potential after only 25 years of life. So this brings us to the conclusions. So clearly, the graphs go to show that the 60 cohort grew more rapidly than the 80 cohort, directly because the ditches caused all the energy that those trees produced in the year to go to growth, so that it did not get outcompeted by other competing trees. And both cohorts actually did reach the genetic maximum growth. However, the 60 cohort reached that much, much, much faster than the older cohort did as a response to the ditches. So this ditching has a couple of issues because commonly people think that faster growing trees mean they're healthier, they're better, it's a better ecosystem if the trees grow faster. That is not the case in this peatland environment because that is a stress response. Their quick growth is a that is their last resort, so that they do not get outcompeted by species like red maple and black gum trees that thrive better in drier conditions. So if these sites got drier, then the Atlantic white cedar would cease to exist because of competitors. And another issue that relates back to the catastrophes of the early 2000s in Great Dismal Swamp, fires. So Atlantic white cedar is a fire-dependent ecosystem. They have seed refugiums underneath the peat soil that are protected by water levels. So when the water level is normal, not ditched, a fire can come through, wipe out previously existing trees, and then those seeds that are stored in the peatlands can then sprout and grow take the place of those older trees that were killed in the fire. However, in the drained Dismal Swamp, the fires of 2008 and 2011 caused all of those seeds to be burned because the seed refugium was damaged in the fires. So that concludes why the ditching is a stress response and not beneficial to the overall environment of Atlantic white cedar. So that is all I have. I would just like to acknowledge Christopher Newport, Department of Organismal and Environmental Biology, for lab space, resources, classes that have allowed me to understand this data. The CNU Center for Wetland Conservation, which is the lab group that has provided me with data and guidance for this project. And of course, U.S. Fish and Wildlife Service for the work they did back in 2003 in terms of collecting and obtaining those samples to study. Thank you very much. That is all I have.